So we have John Stupin about connections between orthogonal arrays and the optimal design.
Well, thank you very much, and thank you for all of you still being here. The last speaker on the last day. I was wondering, kind of, how did I get in that position? And,
because I'll tell you why. Because I know you're a bloody good speaker, and I
so that was one of my theories, that maybe Rosemary thought we'll wait with the best until the end, right? But I also have some other theories that, where can we hide this guy, right? So whatever the reason is and whatever the strategy was, it's a pleasure to be here, and thank you very much for the invitation and for putting up such a great event. So this is joint work with one of my students, or one of my former students, G2 10. And I should say that I've been department head for many years and recently moved to another university, and so all of these things made that I couldn't spend as much time with my students as I wanted to. So this work is essentially my students' work, and I just had the honor to present it here. In order to tell you what we did, I have to give you some background first, so let's start with that. It's going back to a 2009 paper by Min Yang and myself, where we considered generalized linear and nonlinear models with just two parameters, so very simple models. And also only one design variable, x, that takes values in some interval. So later work has generalized this first part more than two parameters, but has not really generalized this second part more than one design variable. So what we used there is we used the approximate design setup, as you have seen in other talks as well. So we have design points x1, x2 with corresponding weights. And we focused on locally optimal designs, but not on a particular optimality criteria, but what we were hoping for is come up with so-called complete class results under the loner ordering. And what that means is that if you give me an arbitrary design, let's say xi, and I compute the information matrix under xi for theta, then I want to have a small class of designs, and I want to be able to search in that small class of designs and find a design there that's better under the loner ordering in terms of the information matrix than the design that you gave me. So if you give me a design xi, I want to go to a small class, capital Xi, where I can find a design xi naught star that under the loner ordering beats your design. All right, so that's the completeness. Such a class of designs is called a complete class of designs, or sometimes an essentially complete class of designs. So that's what we were looking for. Can we find such classes? And of course, such classes exist. I mean, there is. Before going to that point, first let's observe that if you're looking for a d-optimal design, the implication of this would be that you can just look in this small class of designs for a d-optimal design, because if I can always find a design that's better on the loner ordering than your design, then I can also find a design that's better on the d-optimality than any design that you give me. And the same is true for any other optimality criteria that's consistent with this loner ordering. And so that's nice, and it means the search for optimal designs can then be restricted to the smaller class. And it doesn't really matter what optimality criteria you want to use, as long as it is consistent with this loner ordering, so as long as it's information matrix based. And such classes always exist. Trivial one would be the class of all designs, but of course Carat-Theodoris theory can also be applied here to give you a smaller class than the class of all designs. But we were hoping to find even smaller classes than that. So among others in that paper, what we looked at were generalized linear models where we define C as theta 1 plus theta 2 times x, so have a linear predictor, and theta 2 is not equal to 0 here, And since we're using local optimality, we have guesses for theta 1 and theta 2. So there's a one-to-one correspondence between C and X. And I said X was restricted to some interval. So C is also going to be in some interval. Let's say C is in the interval from L to U. And what we proved is that if you use a logistic or a probit link with the linear predictor C, then the complete class consists of designs with only 2 support points, where you have all these different specifications as to what those 2 support points are. And I know that this should work, right? I saw it in action just a moment ago. All right. So if the upper endpoint of this interval is less than or equal to 0, then you know that one of the 2 design points you can take as this upper point, U. If the lower point of this interval is positive, then one of the design points you can take it as L. So there's only a second design point plus the corresponding weights that are the unknowns. And in these 3 cases, talk about the situation where 0 is in this interval. And so these are different cases. And you either wind up with symmetric points, 2 symmetric points, or you wind up with one point being the endpoint, either L or U. So there's a specification. It's a smaller class than you would get from Carr-Theodori's result. But it specifies at most 2 design points, and in some cases it tells you what one of the design points is. And so then you only need to find one other design point plus the corresponding weights. And if you want to summarize these 5 different conditions, then I think it can be summarized in this sentence. The 2 points are symmetric, or one of them is the endpoint that is closest to 0. So that's the class, complete class of designs for these models, for these simple models with only 2 parameters, logistic or probit link on the generalized linear models. Okay, so that's the result that I'm going to use in just a little bit. So then in the 2012 paper, we asked the question, what happens if we add classificatory variables or factors to it, or you know, if you consider groups. And so if I have 2 factors, each at 2 levels, then that generates 4 different cells. And so my design now is going to look like a combination of x's and omegas, but I have to specify not only what value of x I take, but also in which class I take that particular value of x. Right? So I can have some points in the class 1, 1. I can have some points in the class 1, 2, some in 2, 1, some in 2, 2. So I have 4 different classes, and I have to specify for each of those classes which values of x I'm going to use. So design becomes a little bit more complicated in that sense. We didn't add any constraints to the cells on you know, the weight, the total weight for a particular cell, or any weight for the marginals, but you certainly could do that. For example, if you say that 30% of the observations have to come from cell 1, 1, then you would have a constraint of this nature. So you could add such constraints to the problem, and in some cases that might be more appropriate to do. But that's not the problem that we considered. We looked at the problem without any constraints related to these cells. So the omegas, the weights, are free. You can choose them whatever way you want, whatever ways you think is best. And so then you have to ask yourself, well, what kind of model are you going to use now, and what are the parametric functions that might be of interest? So I'll tell you what we did. So in general, if there are f factors, and the kth factor has sk levels, then the product of all these levels is, of course, the number of cells that you get, and I'll denote that by s. And the model that I'm thinking about, if I have an exact design, then I would, so I have a binary response, yij is the jth binary response for the ith cell. Then I would model that maybe as some probability of alpha 0 plus alpha I plus beta times x, or some function of alpha 0 plus alpha I plus beta times xij. So P is the is the inverse link function for this problem. So I have for each cell, I have an alpha I, and for each, I have a common slope beta here, although you could also look at the model where you have for a different slope for each cell. So it's clearly an over-parameterized model. As I just pointed out, you can use a beta I over here, which actually we did in the paper, but I'm not really going to use that in this talk very much. You can model these alpha i's. I have now one alpha I for each of the cells, but of course I can model them using main effects and maybe main effects and two-factor interactions and so on. And so I can simplify the model in that way. And in terms of notation, I'm using I here to denote the cell, but in many cases I will use this notation, this more intuitive notation, I1 to IF, where each just indicates the level at which the first, second, and so on factors are for that particular cell. So the entire parameter vector is going to look like this. I have the alpha 0, I have alpha 1 through alpha s, one for each cell. And then I have a beta here that is either a scalar if I use just a single slope parameter, or that's a vector if I use different slope parameters. I defineCij's in this way, and rather than formulating the design problem in terms of the x's, I'm going to formulate it again in terms of the c's. So Cij is essentially the value of the linear predictor that I'm going to use in my generalized linear model. And so it's either with a fixed scalar beta or with a vector or with a beta I over here, depending on which model that I use. But again, I'm pretty soon I'm just going to restrict myself to this model where I have a fixed beta. And so now I have all these different cells, and for different cells I would have different design regions. So I'll call them Li to Ui. This is the design region for the ith cell. So then, for the logistical probit link, what you can show is that a complete class is formed by all the designs with at most 2 support points per cell, and with additional specification of the same type as I showed you earlier when I just looked at the model for 2 parameters. So you can specify that one of the points is the endpoint for that of the design region for that particular cell. So it's still a nice result that you have a relatively small complete class, 2 design points, at most 2 design points per cell. But if you have a large number of cells, then that's still a large number of possible design points. So it's helpful, but maybe not as helpful as previously. The proof is rather simple. So this was done in this paper, 2012. So the proof is rather simple and uses an additivity property of the information matrix, where you can really write this as a sum of information matrices for individual cells. And of course this result, I'm specifying this result here. Well, this result remains true if the model is simplified by modeling the alpha I. So if you make that model simpler, then that complete class is still a valid complete class. Now, if you have different slope parameters, different beta i's, then in order to learn something about those beta i's, if you're interested in estimating those beta i's, in order to learn something about them, you're going to need at least 2 observations per cell. So I just told you that the complete class consists of at most 2 points per cell. If you're really interested in all of these beta i's, you can't do better than that. You're going to need at least 2 observations per cell. So then you can restrict your attention to designs that have exactly 2 observations per cell. I'm not going to look at that case. So I'm going to drop this. I'm going to look at a common slope parameter beta. Also, if the alpha i's are not simplified, then even if you have a common slope beta, then in order to learn something about this alpha I, you're going to have at least one observation from each of those cells. And otherwise, you're not going to learn about all of the alpha i's. So if as part of the objective you want to learn about things like alpha 0 plus alpha I for every I, you're going to need at least one observation per cell. And you cannot get away with not making observations in some of the cells. So I'm not going to look at that situation either. I'm not really interested in that either. So I want to simplify the alpha i's. So in the remainder, I will focus on the common slope model with simplifying assumptions for the alpha i's. Because what I'm hoping for is that I can look at a complete class that has fewer support points. Right now, I need perhaps as many as 2 support points in each of the classes. I'm hoping that I can ignore some of the classes, that I don't have to take observations in all of the classes, and still can find an optimal design. So continuing with the background based on this paper. So for a main effects model, the alpha for cell I, for cell I1 through IF, can just be written as a sum of alphas, where essentially all of these guys correspond to main effects of the different factors. And we decided to look at the vector eta 1, which is really a maximal factor of estimable functions, and the one that we chose, because it's obviously not unique, the one that we chose is simply the value of the linear predictor when x is equal to 0, and then comparison between all of the levels, comparing all of the levels to the first level here for factor 1 and over here for factor f, and then the slope parameter beta. So that's a maximal vector of estimable functions. And we also looked at second parameter vector eta 2, where we assumed that just cross this guy off and look only at the comparison of the levels and at the slope parameter. Now, of course, you can look at other functions than these, but these were the particular ones that we decided to look at. And we are going to focus on a particular optimality criteria, namely on d-optimality. So from that perspective, it doesn't really matter if you're going to use a maximal factor of estimable functions. It doesn't really matter which one we use. So if there were no restrictions on the design space, so for every cell we can take whatever C we want, then what you can show is that the optimal designs for these parameter vectors, eta 1 and eta 2, consist of, or at least a d-optimal design is given by a design that makes observations at 2 points, C star and minus C star, in each of the cells, and that uses equal weight. So it's uniform on its support. So it has exactly 2 design points in each cell, C star and minus C star. And it's uniform on its support. And the C star is a maximizer of either this function or this function, where this psi is a function that comes up in generalized linear models all the time. It's the derivative of this function p, this inverse link function p squared, divided by p times 1 minus p. And this value of m over here is the sum of levels minus 1. So you find a C that maximizes this. That gives you an optimal design for eta 1. You find a C that maximizes this. The only difference is that this exponent is decreased by 1. So you find a C that maximizes this, and that gives you an optimal design for eta 2. But it's a large design if you have a large number of classes. Right? It has 2 design points in each class. And it's just a main effects model, so I don't have that many parameters. So I could hope maybe to get away with smaller design than using 2 design points in each class. So So this was with no restriction on the design space. Well, if you have a restriction on the design space, but it happens that C star and minus C star fall within the design region for each class, then these designs are, of course, also de-optimal. So it depends what the restrictions on the design regions are as to whether you could use these designs or not. So the work that I started with my student, or the problem that I gave to my student, is to think about, these designs have 2 support points per cell. And also we looked at algorithms, by the way, earlier this week. Algorithm by Young and Biederman and Tang was mentioned as a cutting-edge algorithm. We tried that algorithm, this problem, and the algorithm has difficulties with this problem and also tends to come up with large number of design points. So I wanted to ask my students, and it's a very modest goal, for a main effects model, can we reduce the number of support points by using an orthogonal array? And an orthogonal array, here's a definition. So it's an array with n rows, with this many, with f columns, and within the kth column you have the symbols 1 through sk, and it's called said to be an orthogonal array of strength t if it has the property that if you select any t columns, then look at the rows of the subarray that you generate by selecting these t columns, and in those rows you should see every possible combination of the symbols that can occur. All of them should occur, and they should occur equally often. So the hope was that by using an orthogonal array that I could restrict myself, or that we could restrict ourselves to using only the cells corresponding to the level combinations that we would obtain from this orthogonal array. And that in the other cells, we could ignore them. We wouldn't have to take any observations there. That's what this says. And of course, then we would wind up with 2 times n support points rather than 2 times s, and of course that's useful if n is indeed less than s. There's never a guarantee. Whether you can find an n that's less than s depends on what these values s1 to sf are, and what the strength of the array is that you want. But in many cases you can find something where this capital N is less than s, so you would wind up with a smaller design. So this idea works for a main effects model and for the logistic and probit links when using an orthogonal array of strength 2. So this value of t, we can just take it as 2 when we have a main effects model. And that's very, very similar to what one sees with linear models. So here's a statement of a result. So for the logistic and probit link, if you have a main effects model and interested in these parameter vectors eta1 and eta2, then design that places, again, it's uniform on the support points, that uses the same support points, C star and minus C star in the cells, but not in all of the cells now, but now only in the cells that you obtain from your orthogonal array. So some of the cells will be empty. There will be no support points at all. If you use that design, then that's also a de-optimal design for, or those designs are de-optimal designs for eta1 and eta2. Because the difference between the 2 designs is only that you get different values for C star and minus C star, as described earlier, as the maximizers of these 2 functions. Proof is not that hard. In fact, what you can show is that with this design and the design that uses 2 observations in every cell, you actually get exactly the same information matrices for theta. And these information matrices really depend on these expressions, these 6 expressions. And you can show that they are the same whether you use the orthogonal array-based design or whether you use the design that uses all cells. And you can the reason that you need something like an orthogonal array comes from, for example, this expression over here. In order to keep this the same, here the summation is over j, which means the replicate or the different support points within a cell, and it's over I, that means over the cells that you're using, but it specifies that you only sum over those cells that have a fixed level for the kth factor and for the k prime factor, right? You take two factors, for those two factors, you fix the levels, and now you sum only over those cells where those two factors are fixed. And that's where you need the orthogonal array property to show that when you do that, you get exactly the same as when you sum over all possible cells for the two types of designs that we have just described. So without the orthogonal array property, you wouldn't have the property that a sum like this with these restrictions would be the same for the design that uses all cells and for the designs that uses only the cells corresponding to the orthogonal array. So some benefits of orthogonal array-based designs in this way: smaller support size, 2n versus 2s points. They correspond to more exact designs. So, I mean, here you would have to multiply by 2n to get an exact design. Here you would have to multiply by 2s to get an exact design. So, they're the more exact designs that you can obtain that are optimal, that would be optimal. And they can exist with more restrictive design spaces, because the restriction on design space is now only needed for those cells that are actually identified by the orthogonal arrays as the cells that you should be using. The other cells you don't have to worry about what the design space is, because you're not going to use any points in there. So that's nice, but it turns out that you actually can do better than that. That you can still find smaller designs than the ones that I just described to you obtained from the orthogonal arrays. So still assuming the main effects model, if there is an orthogonal array where, again, of n rows, I have the same stuff over here, f columns, with the number of symbols in each column equal to the number of levels for that particular factor, but I added another column to this orthogonal array. I should be able to add another column to it, a column with 2 levels. Suppose I can do that and keep it of strength 2. If I can do that, then there are actually designs that use only n support points. Again, uniform on the support points. So rather than 2n, which I had at the time that I didn't have this 2 over here, I can now actually go to n design points, and they give me a d-optimal design for eta 1 and eta 2. And how to obtain such designs? Turns out that you can use C star in half of the cells and minus C star in the other half of the cells. And which cells are you going to use C star in? Well, that you determine by this additional column that you have now in your orthogonal array, where you see a symbol of 1, you use C star. Where you see a symbol of minus 1 in that column, or sorry, a symbol of 2 in that column, you use minus C star. And that design turns out to be d-optimal. So now only a single point needs to be in the design region for each of the n cells corresponding to the first f columns of this orthogonal array. And again, it's less of a restriction on the design space. So here's a small example, kind of a toy example. Suppose I have 2 factors, each with 2 levels, and I take an orthogonal array that has 2 levels, but it has an additional third column with 2 levels. So here it is. This is an orthogonal array. And so what I would do is the first 2 columns, they tell me what the cells are, 1, 1, 1, 2, 2, 1, 2, 2, right? And the third column tells me whether I should take C star or minus C star. So wherever I see a 1 over here, I take C star. Wherever I see a 2 over here, I take minus C star. And that gives me a d-optimal design. So in this toy example, I did not reduce the number of cells because I still need observations in all of the 4 cells. In general, by using an orthogonal array, I can actually reduce the number of cells. But even in this toy example, rather than using 2 points in each of the cells, I reduce it to using only 1 point in each of the cells. So even in this toy example, there's a reduction in terms of the size of the optimal design. Now, if you can't add a 2-symbol column, then sometimes it's possible to add a column with an odd number of symbols. And by a very similar idea, you can actually also reduce the size of an optimal design there as well. So I'm assuming here that I cannot add a 2-symbol column, but I can add a column with an odd number of symbols, let's say 2u plus 1. And what I would do is that for u of the symbols in this column, I'm going to use a C star. For u of the symbols, I'm going to use a minus C star. That takes care of 2u of the symbols. And for the last symbol, I use both a C star and a minus C star. And so there are some cells where I would use 2 observations, namely corresponding to one of the symbols over here. And for all of the other cells, I use only 1 observation in those particular cells. And then you come up with this number of support points as shown over here. If you do it this way, it's actually not uniform on its support anymore. What you need is that each of the cells you have a fixed weight on, a weight of 1 over n. So what it means is in the cells where you take 2 points now, you have to split that weight as 1 over 2n on each of the 2 points. And you can show that if you actually have an orthogonal array of slightly higher strength, that you can still, even in this situation, take only 1 point per cell. So we also looked at, well, what if you have more complicated models? If you have interactions as part of your model. And the results are very similar, so I'll go through this very quickly. So I'll keep it simple in terms of the models. I'm not going to add some 2-factor interactions and not others. I'm only going to add, if I'm going to add 2-factor interactions, I'll add all of them to the model. If I'm going to add 3-factor interactions, then I'm assuming the main effects and 2-factor interactions are there, and I add all of the 3-factor interactions and so on. Because I need to look at different parameter vectors, eta, and I'm just going to look at maximal ones. And then look for d-optimality. It's a little bit more difficult because you don't have a d-optimal design here. There is none in our 2012 paper that only looked at d-optimal designs for main effects. And we were not able to directly come up with maximization of the determinant of the information matrix for eta on these models. At least my student was not able to do that. But he found another way around it by using equivalence theorem. So he guessed the form for the optimal design using all of the cells, and then theoretically verified that his guess was correct using a generalized equivalence theorem. And the conclusion of that was that the optimal designs have the same form as for the main effects model, but now with a different value for C star, there's a maximizer of C squared times the psi function to the power r, where this r is now equal to the rank of this matrix B in this parameter vector. Eta is B times theta. So this requires again that C star and minus C star are in the design region for every cell, and otherwise, of course, you can't use this design. And as for the main effects model, orthogonal arrays, but now of higher strength, you can't use strength 2 anymore, can be used to reduce the number of support points. And so what you have to use if you have interactions that go up to t-factor interactions, then you need to use an orthogonal array of strength 2t in order to come up with optimal designs. And so then you can just use 2 points in the cells specified by this orthogonal array to come up with the optimal design. And you can also go do the same thing that I showed you for the main effects model, come up with conditions under which you can restrict yourself to using only 1 observation per cell. in the cells specified by the orthogonal array. And that's what these lines state here. All right. So let me conclude with a brief summary. O8-based designs can help to reduce the number of support points. They correspond to larger families of exact designs, and they reduce requirements on the design space for the existence of the optimal designs. Algorithms seem to have a hard time for these problems, to find optimal designs, especially small designs. They tend to come up with designs that have a large number of support points. So we focus on de-optimality. Obviously, you can look at other criteria, and maybe possible to do similar things to other criteria. We focus on no constraints on the cells, but as I said, that may not be, for some problems, that may not be the right thing to do. Maybe sometimes it's actually quite natural to use some constraints on the different cells. These models tend to have a large number of parameters, and to some extent, of course, that reduces the appeal of using local optimality, because you have to make guesses for a large number of parameters. On the other hand, I think other approaches also face challenges if you look at models with such large number of parameters. So we continue to focus on local optimality. I'll leave it at that. Thank you very much.
Question?
It's time to go home.
Well, as I mentioned in my talk, one of my students has generated de-optimal design using PSO for Poisson models with up to 5 factors, including all 2-factor interactions. I think it should be able to apply and give some insights into similar problems.
Yeah, I would be interested to see what the algorithms would come up with, and whether. So I'm sure they can come up with efficient designs, but and I would be interested to see whether they also come up with designs with a relatively small number of support points, or whether the support points turns out to be relatively large.
So let's thank. Oh, sorry.
I'm sorry, this is not a technical question. It would never have occurred to me to think that something nice like orthogonal arrays could help in this problem. How did you make that decision?
Well, if you look at the designs for the de-optimal designs that we found theoretically that have observations in each of the cells, I mean, they have a very nice structure. They use in every cell, they use minus C star and C star. At the same time, it gives you a number of support points that seems to be way too large for the number of parameters that you would have in your model if you just have main effects over there. And so then the question automatically became, well, can we make observations just on some of the cells rather than all of the cells? And well, what are you going to use to get? So orthogonal arrays was a natural thing to look at, I think.
Why are you concerned about having too large number of support points? Criticism is always you can't check your model, so have more support points is a good thing.
Right. So I gave you some reasons, I think. Let's see. So I guess one is you get more exact designs that are optimal by having a, especially with these designs. I mean, if n is a smaller value than s, which is typically going to be the case, then there are more exact designs that I can come up with that are optimal designs than if I use the designs that we had originally that had 2 support points per class. And the other thing is that I don't have to worry about the design class the design space in every class anymore. I only have to worry about some of those now, so it's less restrictive in terms of the design space.
So you actually found the exact D-optimal designs for this model?
Well, you know, it's an approximate approach, but my weights are all 1/2n, so if I have a number of observations that's a multiple of 2n, then I have exact designs. Yeah.
And so if n is small, you've got more chance of doing that.
That's right.
Yeah.
Let's thank our speakers in this session.